So, last time we talked about 4 velocity and 4 momentum. 4 velocity we defined in terms of 3 components of what we called proper velocity, eta symbol we used, and we defined it like eta, which is called proper velocity, as gamma times the ordinary velocity. So, if a particle is moving in some frame S frame with a velocity u, then corresponding to this velocity we define this quantity eta and we call it proper velocity. And you remember we defined eta x as dx d tau, then eta y as dy d tau, and eta z as dz d tau. And what was this d tau? This d tau was proper time interval between 2 events, and the events were the particle is here at time t and then the particle goes somewhere else at time t plus dt. And this location is x y z, and this location is x plus dx, y plus dy, z plus dz. So, this is the location. So, these are the 2 events, and this is the proper time interval between these 2 events. That means this time is measured in the particle's frame, whereas the displacements are measured in the lap frame in which the particle is moving with velocity u. So, that is the kind of hybrid quantity we construct and call it proper velocity, and that proper velocity can be written as the spatial component of a 4 vector, and the first component is c times gamma times c times gamma, and the 3 components are eta x, eta y and eta z. So, this is our 4 velocity or velocity 4 vector. It is a 4 vector, it transforms according to the Lorentz transformation, the same transformations which are followed by position 4 vector ct x y z, the same transformation equations. And remember this gamma, this corresponds to, what is this gamma? This is your 1 by square root 1 minus u square by c square, the particle velocity which is coming here. We will also talk in terms of frame velocities, and there also we say gamma and beta gamma and all those things. This gamma is particle velocity coming here. Okay. Now, we multiply all the 4 components with the rest mass of the particle, which is again a constant. So, m naught times this. So, we construct another 4 vector m naught times c gamma, then m naught times eta x, m naught times eta y and m naught times eta z. So, since this is a 4 vector, this is also a 4 vector, we are only multiplying by the constants, and this we defined as, or we call this 4 vector as momentum 4 vector or 4 momentum. This we discussed in the previous class, and then we said that these 3 quantities are just components, x y z components of linear momentum, right, because our linear momentum is defined as mass of the particle, velocity of the particle. If you write particle velocity as u, then u here and then divided by square root of 1 minus u square by c square, and that is in fact gamma. So, this is m naught times gamma times this velocity, and this is your eta. So, this is m naught times eta, and hence these are components of linear momentum in x y z direction. So, this is okay, this is your px, py, pz, m naught c gamma here, and then px here, py here and pz here. And we asked the question at the end of the lecture that this we understand this is linear momentum x component, linear momentum y component, linear momentum z component. What is this quantity? Is there a physical significance of this quantity? And yes, the physical significance is very much there, and today we will be talking about this quantity. What is this? You write it as p 0th component in our standard symbol. 0th component, first component, second component and third component. So, the question is, what is this 0th component thing? What is this thing, right? So, this is these are all same, okay? These are just symbols are different. Now, to understand this quantity, we will start a new topic, and that is kinetic energy. How do we get expression of kinetic energy if the speeds are not limited to small speeds compared to c? So, let us talk of kinetic energy. You know, in Newtonian non-relativistic mechanics, we know the expression very simple, half times mass times speed square, that is kinetic energy. How do I get this? How do I get this expression in non-relativistic Newtonian mechanics? The derivation starts with work energy theorem. If you have a particle and then you apply a force on that particle, and then there is a displacement of the particle, there is work done by the force on the particle, and the amount of work done by this force on the particle is equal to the change in kinetic energy. That is the definition of kinetic energy. From there we define kinetic energy. So, work done by the force. I am talking of a particle. So, there is one single particle, and then whatever is the resultant force on that, work done by the force is equal to the change in kinetic energy. This is the energy due to motion. Together with, we say that at speed 0, kinetic energy is 0, right. So, if you say that at speed 0 the kinetic energy is 0, and then you define the change in kinetic energy, then you have defined kinetic energy everywhere. So, for a small time interval where there is a small displacement of the particle, the work done dW is F dot dr, and F you can write as dp dt. This equation also holds for relativistic speed. For any speed it holds, dot dr here, and this dr and this dt you can combine together and write this as dp dot v, right. This dr dt is the velocity, let me write it u, particle velocity. V I am reserving for the frame velocity when we change frames. So, this is the work done, and this is change in kinetic energy. So, you can write this as dk, okay, dk. Work done by the force is equal to the change in kinetic energy. Now, in non-relativistic speeds, what we do? We say that for small speeds, non-relativistic, we say that p is mass times velocity. So, this is p, and hence dp is m naught du, and therefore, this dk is m naught du dot u or u dot du. And this quantity, this u dot du is half d of u square m naught. m naught. Okay, so let me write m naught here. So, m naught and then u dot du, that is half d of u square. How do I get this expression? This expression is simple, u square is u dot u, that is speed square, u dot u, and therefore, if you write d of u square, so there is a product of two quantities. So, keep first as constant and then differentiate the second, plus keep the second constant and differentiate the first. So, you get u and dot du and plus du and dot u, and that is 2 times u dot du, and hence u dot du is half of du square. So, that we are using here, u dot du we are writing half d of u square. Now, integrate this expression. The speed of the particle changes from 0 to u. What is the change in kinetic energy? So, we integrate this expression dk, and this side is m naught by 2 m naught, and u dot du is half d of u square, u dot du is half d of u square. So, for this u dot du we are writing half d of u square. So, on this side it is m naught by 2 and d of u square, u going from 0 to u, and kinetic energy will go from 0 to k. At u equal to 0, kinetic energy is 0 by definition, and then at u, when the speed is u, then the kinetic energy is k, and hence it is k is equal to, this side is just k and this side is m naught by 2, integration of this is u square, and then you put the limit u equal to 0 here and u here, and that is half m naught u square. So, this is how that expression of kinetic energy, non-relativistic limit half m naught u square is derived. What we want is lift that restriction, okay, lift that restriction, the speed can be high, up to here it is fine, here we are using that non-relativistic speeds p equal to mu, here we have to make changes. So, if we are in this relativistic region, what we should do is we should use the proper definition of linear momentum, and p is equal to not mass times velocity, but mass times velocity times gamma. Remember, this gamma is the same gamma, this gamma u, particle speed is u, I am using that u to write that gamma. So, momentum is defined as m naught, which is the mass of the particle, times the velocity, ordinary velocity, and times that gamma. So, that I should use here. This is the place where I am first time using the fact that I am talking of non-relativistic speeds. Okay. So, we pick up from here, dk is equal to dp dot u, and what is dp? So, let me write u dot dp, and what is dp? dp is m naught is constant, so I can write this m naught here, and here u is here and u is here, again there is a product, and therefore it will be u d gamma and plus gamma du, right. This is product of the two functions, both are functions of u. So, u d gamma plus gamma du, and then u dot is here. So, this is equal to m naught, and then u dot u, which is u square d gamma, u dot u is u square d gamma plus this gamma here and u dot du here, u dot du here. Now look at this d gamma. Your gamma is square root 1 by 1 minus u square by c square, or 1 minus u square by c square power minus half. So what is d gamma? First you differentiate this minus half here, then 1 minus u square by c square power minus 3 by 2 here, then you differentiate this, and when you differentiate this you have minus 1 by c square, minus 1 by c square. You are differentiating this with respect to u, so minus 1 by c square u square. U square, when you differentiate, you get 2 times u dot du. We have already done here u square. When you differentiate u square, you get 2 times u dot du. So that is here. So this minus will cancel out with this minus. This 2 in the denominator will cancel out with this 2 in the numerator, and you are left with 1 minus u square by c square power minus 3 by 2, and then you have this 1 by c square and u dot du. What I am going to do, I will write the expression for u dot du from here and put that in place of this u dot du. Okay. So let us write what is u dot du from here. U dot du is equal to, d gamma is here, this c square goes here, so c square d gamma, and then this whole thing goes here, so 1 minus u square by c square power 3 by 2, that is u dot du. So that I am going to put here, or let me multiply by gamma also. So what is gamma times u dot du? It is this, right? Gamma times u dot du, it is this, and that is c square d gamma 1 minus u square by c square power 3 by 2, right? 3 by 2, it has come this side, and then gamma, this gamma is 1 divided by square root of u square by c square. This gamma I am writing 1 divided by square root of, this is square root 1 minus u square by c square, and so this half power and this 3 by 2 power, they will simplify. It is c square d gamma 1 minus u square by c square. Take this c square inside, it is d gamma c square minus u square, and put it here in the expression of dk. So what is dk? dk is equal to m naught and then u square d gamma, this is u square d gamma, and then plus this expression, and this expression is here, it is d gamma c square minus u square, c square minus u square, and then d gamma, and u square d gamma here and minus u square d gamma here, they cancel out, and you are left with a very simple expression, simple looking expression, m naught times c square times d gamma. This is constant, this is constant, and you just have d gamma. So after that, what did we do? After getting all these things, we integrated from 0 to k and u going from 0 to u. Same thing here, integrate. dk is equal to m naught c square is constant, and therefore this is just d gamma. This is 0 to k, and this is u going from 0 to u going to u. So at u equal to 0, there is some value of this gamma, and at u there is some value. So you have to integrate between these limits, and here correspondingly kinetic energy is 0, here kinetic energy k, and therefore this is m naught c square, integration of d gamma is just gamma. So, it is gamma at u equal to u and at u equal to 0. What is gamma at u equal to 0? Gamma at u equal to 0 is just 1, right. If u is 0, here if u is 0, gamma is just 1, and if u is u, then it is just this. So, what is the expression of dk? Let me write it here before I rub the board. This k is equal to, this integration k is equal to m naught c square, and then within bracket 1 by square root of 1 minus u square by c square and minus 1. This is the expression, this is that kinetic energy expression that we are looking for. Okay. So, let me clean the board, write this expression again and start discussing on it. So, the kinetic energy expression is k equal to m naught c square, then square root of 1 by 1 minus u square by c square minus 1. This is the expression for kinetic energy in place of half m naught u square. Okay. So, be very clear about this, that your so called relativistic mass will not work here. In non-relativistic mechanics, in non-relativistic limit, k is equal to half m naught v speed square. If you say that okay, in place of rest mass, the mass increases because of velocity, and therefore we have to put that increased mass here, that relativistic mass here, and you modify this as half m times u square, which is m naught by square root 1 minus u square by c square and times u square. It will not work, it will not work. This is not same as this. So, the concept of relativistic mass, once again I emphasize, is for limited use. Linear momentum, yes, your definition is P equal to mv. In place of rest mass, you put that relativistic mass, you get the right expression of P. But kinetic energy, no. So, for very limited purposes, this concept of increase in mass with velocity etc. can be utilized. So, do not give too much of importance to that mass. Your mass is just one mass, that is mass of the particle, right. It is a property of the particle, and then in terms of that mass you write whatever expression it comes. We will see that this finally reduces to this. If your u is small, it is very simple algebra one can do and check that it does reduce to this. So, this is the right definition of kinetic energy. So, once again take this, let me write this as k equal to m naught c square divided by square root 1 minus u square by c square and minus m naught c square, just opening the bracket, and then take this to the left side, k plus m naught c square is equal to m naught c square here, square root of 1 minus u square by c square here. And this quantity is relativistic mass. If you want to write that, m naught divided by this is relativistic mass, and then c square, mc square, and this quantity kinetic energy plus m naught c square, this we define as, we define another physical quantity, we define it as total energy, we call it total energy and use the symbol E for this, total energy. This is called rest mass energy. This quantity m naught c square is called rest mass energy. we are defining the terms. The physical significance we will discuss later, but we are just defining the terms. m naught c square is called rest mass energy. Capital K is kinetic energy that we have derived. So, we are not defining it as such, we have derived this is the expression, and then kinetic energy plus rest mass energy K plus m naught c square, this we are defining as total energy E, and then this expression is written as E equal to mc square. The very famous equation E equal to mc square, the logo of special theory of relativity. You look at books on special theory of relativity or books on Einstein, and you may find that okay, in a very decorative way E equal to mc square is put on the cover page and so on. So, it is this expression which comes from here. Now, we do have a lot of significance of this rest mass energy and total energy, we will talk about that, but let us go to the original question, the 4 momentum. Let us look at 4 momentum once again, and in 4 momentum you had these 3 components were px, py, pz, and this component here was m naught times c times gamma. And if you see from here, it is E is equal to m naught times c square times gamma, right. This is m naught c square and this is gamma. So, this is gamma, and here the 0th component is m naught c gamma. So, m naught c square gamma here, m naught c gamma here. So, it is nothing but capital E by c. This is nothing but capital E by c, total energy by c, px, py, pz. That is your 4 momentum, that is your 4 momentum or momentum 4 vector. So, these 3 components give you momentum and the 0th component gives you total energy, capital E by c is here. So, that is the expression. This is a 4 vector, it transforms like that CT XYZ, the same Lorentz transformation. If you are changing frame, so in primed frame, let us say these are the quantities. Now, I am changing frame, going to S prime, from S to S prime, moving with velocity v, and then there is a gamma corresponding to that v, and then you know what is the Lorentz transformation. It is gamma minus beta gamma minus beta gamma, gamma 0 0 0 0 0 0 1 0 0 0 0 1, that is Lorentz transformation, and then in S frame the total energy is E. So, E by C here and then Px, Py, Pz here. Okay, so this is how they will transform. If your frame is moving along the x axis, you know how to write Px prime in terms of these, Py prime will be equal to Py, Pz prime will be equal to Pz, and how to write this E prime in terms of these. They get mixed up, energy and momentum get mixed up. Okay, there the time and space coordinates were mixing up in Lorentz transformation, x, y, z, and that t, x and t, they got mixed up. Here correspondingly energy, total energy and momentum, they will get mixed up. So, we will talk more about rest mass energy, kinetic energy, total energy, conservation of energy, all these things in the coming lecture.